Hello, welcome to the Kasm Technologies Solutions Architect course. In today's course, we'll do a brief overview of the Kasm Workspaces, the role of a solution architect within a Kasm deployment, important scoping questions that need to be answered, architectural principles, diving deeper into the individual components that make up Kasm. We're going to walk through some deployment architectures from small business to enterprise single region and enterprise multi-region. And then we'll conclude today's course with a multi-server demo deployment. To start with, what is Kasm? Kasm is containerized remote applications and workspace platform. It provides secure containerized environments, scalable for multi-user support, seamless remote access through a browser, course benefits, enhanced security from remote work, enforcing DLP type restrictions, simplified management, and of course, cost-effective scaling with the ability to auto-scale environments based on user demand. The solutions architect role in general is responsible for understanding client requirements, designing a scalable and secure architecture of Kasm, as well as collaborating with DevOps security and operations to ensure that the final design fulfills all requirements. Key skills include cloud architecture and networking, understanding how container technologies work, both Docker and Kubernetes, just as an example, and of course, understanding of security best practices. When scoping Kasm, there's some fundamental questions that need to be asked. To start with, how many users are you anticipating? Both overall and general, but also more importantly, how many at any given time? What's the max at any given time we're looking to support? Because that will ultimately guide all of our sizing requirements based on what that demand at peak hours is going to be. Second major question, is your company global? What regions do you need to support? Does Kasm need to be available in all of those regions? Is it acceptable for a user to be in, say, Europe, but connecting to a US-based Kasm deployment? Is that acceptable user performance? Or would we like something a little bit more tailored and unique and global in nature and allow them to connect to resources with lower latency closer to home? Additionally, do you have any persistence or file sharing requirements? Ideally, we would probably need to come up with a solution here if the user does want to save configurations and files locally, whether that be as part of their profile, much like Active Directory, or if we're going to connect in user share space, again, S3 bucket, OneDrive, Google Drive, something like that for sharing items. Also, when we start talking about persistence and file sharing, from a security standpoint, if we're going to enable things like session recording, screen recording, where is that artifact going to be stored? Where's that object bucket going to be stored at? Based off of the user's feedback, we're going to need to figure out where this fits in. What things do we need to plug in to achieve that persistence and file sharing requirements? Next big question, what cloud will you be using? Maybe the customer in question has a preference on a cloud provider. Maybe we need to serve up and recommend a cloud provider. But ultimately, if they have an established comfort level with a particular provider, maybe we should lean towards that. But fundamentally, what cloud do you want to use? Is there any existing infrastructure that Kasm must interact with? Any legacy, either on-prem servers or, again, other servers within the cloud? Again, if we're talking about that persistence or file sharing from a team perspective, are there any of those type items that we need to connect with? Next one's a biggie when we start talking about the database, right? Will you be reusing any existing resources? So do you already have a cloud database? RDS, Cloud SQL, VPN transit gateways, DRGs, any network resources. Like, are we going to re-leverage any of those in our new deployment of Kasm? If so, like I said, we need to account for that, and we won't be then deploying out. In the case of the database, we won't be leveraging the containerized SQL or Redis instances. We will be leveraging existing databases and then deploying onto them. Are there any security or compliance requirements? NIST, CIS, etc. Again, those could have implications as far as access controls, additional layers of security, possibly additional software needing to be deployed onto the host. Do we have any other agent requirements? Because the other thing about the security compliance items here, right, is they're going to drive up resource requirements, and we're going to need to account for what the additional load is on those systems when forecasting what size servers to build out for this infrastructure. Next step here is, what are we looking at in the way of high assurance, failover, reliability requirements? As we kind of hinted on the last slide, specifically I'm referring to the database, right? Are we going to just take and have automated backups? Are we going to have a hot Postgres Redis failover ready to restore to? Are we going to set up that cloud service and essentially offload the responsibility of that database onto another provider? But how do you want to account for that? What is an acceptable amount of risk for the customer? Next, of course, do we have any best practices within the organization? Things like Terraform, Ansible, once again, kind of bringing in that security software perspective. Is there anything in particular we want to deploy with? For Ansible and Terraform, it's really coming down to how do we want to deploy out Kasm services? Do we want to have Terraform do the whole infrastructure as code business and be able to move that around? Do we invest the time in setting that up? Are they more of a traditional company and they just want to run Ansible scripts to deploy out these services and they'll build out the infrastructure by hand? But really, where's their comfort level at with this? What are your Kasm logging requirements? Kind of gets back around to CIS NIST requirements, right? Do we need to increase session recording for auditing? Do we need to incorporate a SIM? Do they have an existing SIM that they would like to forward logs to? Again, from our standpoint, anything that's capable of ingesting JSON logs will work for us. We'll get into specifics, but I'll say spoiler in the fact that right now our logging by default actually occurs within the Postgres database. For small businesses, medium-sized businesses, that's okay. But when we start getting up to enterprise level items, or if we have any long-term requirements for storing logs, then those need to be offloaded, ideally to a SIM. Lastly, kind of a big one, and that is, how do we handle Windows, right? Of course, on the Linux standpoint, there is much of those resources, of course, are free, right? So we don't really need to contend with licensing. But if you're going to host out Windows workspaces and connect through, what are we going to do with that? Do we need to leverage hardware pass-through, right? CAC, YubiKey, security auth tokens, anything like that? Do we need to forward that traffic, that functionality, I should say, through to the ultimate, end RDP workspace, right? Because that's going to have a bearing on whether or not we can leverage the guac service within the proxy server, or connection proxy server, that is, or if we need to leverage the full-blown RDS gateway and do a thick client through, so we can leverage those, not only the DLP controls of Kasm, but also forward that USB pass-through and security aspect. And then, of course, how do we handle Windows licensing? Are we going to bring our own licenses, or are we going to consume a cloud service that is going to not only provide the Windows workspace, but also licensing for it? But how do they want to contend to handle that? All of these questions are going to ultimately guide where we go with the rest of our solution architect journey. So now let's dive a little bit deeper into Kasm and the roles of Kasm servers within the product. So in general, I'd say there's 5 roles that exist within Kasm systems. You can see here, database, web app, agent servers, connection proxies, and then dedicated proxies. So to start with, let's talk about the database server. When the database server gets deployed, again, if we're not connecting out to an existing external database that's pre-existing within a customer environment or a cloud-hosted system, The Kasm install process is going to spin up 2 containers. One titled Kasm_DB, which is a Postgres instance, and the other being the Kasm_Redis server. Now, Redis in general is used more for shared services, communication, could be expanded on and used in the future, but the biggie on this one, of course, is the Kasm_DB. Again, the functionality of these, especially the PostgreSQL, right, is stores all of the workspace configurations, user data, as well as all the session metadata. Everything that's occurring, not only for the end user, but as for the Kasm platform, is stored within that PostgreSQL database. So again, supported database, PostgreSQL, as well as Redis 5x, right? Again, most important system I would say overall within Kasm is that database. Any service interruption within the database will result in immediately disruption for the end user. For sizing, ideally, 4 cores minimum on the database. 4 gigs minimum for the RAM. 8 gigs is recommended and above for enterprise. Storage is 80 gigs minimum, 100 gigs plus for enterprise. And you can see down at the bottom, sort of a loose-based scaling system on this. So you'll notice as we move up with concurrent sessions, gets back around to our scoping questions. How many users at a time are we planning on being on? So for concurrent sessions, 50 to 200, you can get away with that 480. When we scale up to that next 300, we got to add some RAM and some additional hard drive space to it. And when we scale up beyond 500 users, we really want to bump up the cores as well as the hard drive space. The other big consideration for the storage, as I mentioned before, our default logging location is going to be that Postgres database. So all debug logs are maintained for 4 hours. All other logging is retained for 7 days. If we need extended retention, or if we're anticipating a lot of those log files being created due to user-based churn, we really need to leverage down there at the bottom and enterprise them. We need to offload those. And when we do the offloading of them, we need to make sure we're going into the Kasm console, setting our log retention to 0 so we disable all of the database logging, and we're just leveraging that forwarder. Additionally, from a database best practice standpoint, the database does require care and feeding. So regardless if that is internal within our container image or externally by an external service or an existing database, someone needs to ensure that those tables are being vacuumed up, that the database health is overall good. We're capturing backups. We're making sure we have recovery procedures and everything in place that are actually able to be executed. As mentioned before, strategies for redundancy, high availability, right? Postgres replication for failover, right? Our recommendation is to go down and read Postgres's documentation on how to set up HA clusters and redundancy, but follow their best examples, best practices. Additionally, of course, we can definitely recommend leveraging some service, right? AWS RDS, something like that will automatically scale, provide backups and maintenance for that database server. And then, of course, as mentioned a couple of times now, from a backup perspective, we want to make sure we're at least doing automated daily backups to a secure location, and we have that disaster recovery plan in place with tested and validated procedures. Moving on from the database. Next, web app roles. Okay, for the web app, we actually have 3 containers that get deployed. Kasm API, Kasm Manager, and the Kasm Proxy. Again, functionality here is it provides the actual user interface as well as the admin interface where you're actually logging in, viewing your workspaces, setting up your configurations. And then the APIs for managing the endpoints, the servers within the environment, the related Kasm Workspaces that are being deployed. All of that comes back into this system and is managed through there. So again, key responsibilities, user authentication, session management, and it kind of acts as the central communications hub within all of the services within Kasm. Now, I put kind of an asterisk next to that because if we're talking about multi-region, or we're talking about direct connect through for like RDP or something like that. There might be some cases where it's not quite centrally managing the communication. There might be some points in time where it offloads it, but by default, you might as well consider it the central communications hub. As far as resourcing over here, 4 cores minimum, scales with user count. 4 gigs minimum for RAM, scaling again. Storage is 80 gigs. Mostly all of that storage is going to be for log files and configuration files locally. There's not going to be anything user generated there locally. So resource from a storage perspective is not going to be super high. So again, these web app roles can be scaled vertically and horizontally, however you want to, construct it. But as you can see down here to the bottom, we have kind of 2 deployment types. Standard deployment, which is going back to our previous slide where we're talking about being a centralized communication hub, that would be kind of our standard deployment method. So that's where all the traffic is routing through that web app role server. In that case, 480, right? And then, of course, that could handle somewhere in the neighborhood of 70 to 150 sessions. And if we do direct to agent, you'll notice that concurrent sessions scales pretty high. Now, what direct to agent is, as we step forward, is basically offloading that traffic so it doesn't actually have to pass through and get proxied through the web app role, right? So in this particular case, direct to agent, after the user comes in, gets their UI screen, they're authenticated through, they select their workspace. What ends up happening is the user gets immediately sort of redirected and makes a direct connection from their in space, their in desktop that they're connecting from, through to the agent server in question that is hosting their resource that they're consuming. So there are some requirements here. So if you're going to do a direct to agent connection, you absolutely have to be in a multi-server setup. You cannot do this as a single server. DNS resolution has to be in place. So both the web app and the agent servers must be fully DNS resolvable by all clients. Anybody who's going to connect in has to be able to connect to any one of those resources. All servers must be registered underneath the same domain. Clients and Kasm agents must be able to communicate directly via HTTPS. Not doing any sort of fanciness as far as network is concerned. They need a direct connection via HTTPS. And all of the web app and agent servers must have valid client trusted certificates in order for this to work. So in this picture, we can kind of visualize now what that means. So on the left here, this is a proxied connection. So you can see end users with not only the UI, but also session connections. They come in and hit the web app server. Then the web app server is going to ultimately hand them off to an agent server that their resource that they're consuming is spun up on. And then ultimately that resource can be whatever inside of it, right? But in a direct to agent role, the user comes in, UI is being presented here by the web app. Whatever they click on to consume gets spun up via a session connection directly to the agent in question, hitting those resources. So, like I said, subtle difference here, but that's why we're able to accommodate more throughput on users by going with this direct connection. But again, the thing you must realize here, right? You're exposing more of your resources now openly to the web, right? You're having a greater attack surface in question. This proxied connection approach, you throw a load balancer in front of this. The load balancer is your gateway. Ultimately, right, you can have 2, 3, 4 web app servers on the back side of this, whatever you need to, right? But you have sort of a single entry point here. Whereas this one, you can still have those load balanced web app servers here, still highly recommended so that that's available. But then every single one of your agent servers that are going to host up content have to be directly accessible from the web in order to have this function. So you are kind of paying a penalty for this additional throughput. It's something to bear in mind when you're talking to customers on this. When we start talking about high availability, load balanced N+1 is recommended. Period, right? It'll allow for rolling updates with zero time downtime, right? You can take one of these down and still be able to accommodate your entire user base. So again, going back to our scaling scoping questions, right? For a standard deployment architecture, if we're looking to support 200 concurrent sessions, you're looking at 3 servers for that N+1 redundancy. In total, that could support a total of 450 concurrent sessions with everything up. However, again, during maintenance periods or if there's an outage, that would immediately drop you down to 300 sessions, but it would still handle what your workload, your peak workload would look like. So if we want to start talking about load balancing and what we could support, you can use an application load balancer positioned between the users and the web app servers to distribute load. It would utilize health checks, active or passive, for quick failover. Converges within seconds on failover. Users are pretty much unaware of the server downtime. Also would allow you to put in place things like a WAF, SSL inspection, data logging, any of those additional security requirements. The one con, of course, is it adds complexity as you need to have more components in place within that architecture in order to support this. But that's one way we could go about doing this. Second way would be DNS load balancing, where every web app server has an A record pointing to the same domain. Health checks, again, can be used to automatically remove DNS entries for unresponsive servers. Pros are pretty simple, right? No additional components really required here. It reduces the cost for that resilient services. The big con, right, is twofold. It's slower convergence in the event of a failover. Could be 90 seconds or more for some clients. Also, clients in general might actually cache the DNS entries and then never fail over. Prime example of this would be like AWS Route 53, right? Supporting both on-premise and multi-cloud DNS, right? But that's a prime example of an HA load balancing. Diving a little bit deeper into the health checks themselves, right? Again, they're critical for that HA availability and for whether it be the web app balancer or whether it be the DNS balancer, right? You have to leverage those. So for the web apps, right, we have the /API and that's /__ health check. So that's what you would configure either one of those to get a health check from. So if you go and actually hit that, it returns OK true if it's functional. And it verifies that the API server has an operational status and ensures the API server has access to the database. So that's what's being validated when it returns OK true. Failures, basically anything other than a 200 code is going to be a failure, right? The reason why I don't go down and talk very specifically about what the JSON will return is because it's going to be highly dependent on what the failure code is, right? But basically anything that comes back that is not a 200, just deem that as being a failed health check. Stepping forward again, agent servers. Okay, on agent servers, there's 2 containers that are running. There's the Kasm_agent and the Kasm_proxy. Again, proxy just handles routing that traffic around. The agent container itself, that's the one that's actually responsible for ensuring the correct Docker images are kind of pulled down and available. Also for advertising, what's running where in the way of sessions, right? That's where that entry point is. So again, it manages the containerized workspaces as functionality. Again, deploys and manages user sessions in isolated containers. So resource sizing, completely, once again, dependent on concurrent sessions, the workspaces you're looking to deploy, and how you configure CPU and RAM overrides. So we're going to take a second to kind of walk through some scenarios here. So example 1 here is no override, okay? So in this case, our agent server, our host VM, as it were, has 16 CPUs and 64 gigs of RAM. If we were deploying out a workspace workload, a Docker image, that consumed 2 vCPUs and 4 gigs of RAM, and we did not configure any sort of agent override, then the maximum concurrent sessions that this server could handle would be only 8. And that would, of course, be limited based on CPUs. Even though we have additional RAM that's available, we would be limited by CPUs. So if we step this forward, and now we look at doing a basic, what I would consider to be a basic over allocation. In this particular case, again, same host of 16 CPUs, 64 gigs of RAM, only we're going to put an override in place within Kasm, and we're going to tell it, in reality, you can scale to 96 CPUs and 80 gigs of RAM. And our workspace is now going to be 4 CPUs and 4 gigs of RAM. But in this particular scenario, you could easily support 20 concurrent sessions. Again, the limit in this case is going to be based off of that override of 80 gigs of RAM. Generally speaking, overrides are safe, right? Just like any sort of virtualization technology, really that's where you're picking up some of your benefit, is by over allocating resources. But there's a fine line, and the next one we start talking about that fine line, right? So in this third aggressive over allocation standpoint, we're going to give this server even more resources. We're going to say that the native underlying host has double the resources, 32 CPUs, 128 gigs of RAM. We're going to keep it at that same workspace size of 4 CPUs and 4 gigs of RAM. We're going to put overrides in place of 192 vCPUs and 192 gigs of RAM. That would allow for 48 concurrent sessions, right? Once again, limited by RAM, but you have to be very, very careful. This is more of an aggressive over allocation. And the big thing you want to be looking out for is you never want the RAM utilization to hit near full capacity. And the reason being is the moment you hit near full capacity, we start switching over to using swap space. And swap space is absolutely going to kill performance for any of these workspaces that are being hosted. So we want to push near capacity, but we never ever want to actually hit full capacity of RAM, because there will be a massive penalty as far as performance is concerned and user experience is concerned. So that being said, if we step forward and start talking about the disk space side of this equation, right? The basic requirements for disk on these systems is just 80 gigs. And again, that's for the Docker volume of varlib Docker. We typically use an XFS file system on them. The total size on what we're going to consume is completely dynamic based off of concurrent sessions, as well as the max size allows per user. This gets back again to scoping questions, okay? So if we're going to establish persistent profiles, and those profiles are going to be not centralized, right? If they're going to be locally, or they're going to be dynamically generated while that session is active, those are going to grow in places. So like even things like Chrome, just a browser, all of the cookies and cache for content as users are browsing through it, that all has to be stored somewhere, right? And so that's all going to consume the local storage. Additionally, if we're doing session recording, you have to have a space for the session recording of that workspace to exist locally while it gets encoded and then uploaded to its final location. So there needs to be some more space available to account for that if you're doing session recording. So all of the caveats above, what does that actually break down to being? That breaks down to saying that calculating total space requires knowing the number of users and their expected space requirements. And past that, it's basic, calculations here, right? So total disk space required is going to be that 80 gigs plus however many users times the expected user space. So simple little table here, 80 gigs, 8 sessions, 5 gigs a piece. That's 120 gigs is what we're going to need for sizing on that agent role server on each one of them. Flip side, if you've got more sessions and expecting larger payload, larger storage requirements for those users, that quickly jumps to 280. And our last example is again that 48 sessions at 12 gigs a piece. That's 656 gigs required. Now, one thing I'll tell you, when doing these calculations, if you're using something like NFS for persistent profiles, then we don't have to worry about those persistent profiles being part of this, right? That's all going to be something that gets dynamically mounted in as the user connects in. That's where their profile is going to be stored, along with any of those persistent items. So that's where persistent profiles really come into play. And so again, that won't count in regards to this as long as you're leveraging persistent profiles in that manner where it's going to be offloaded to an NFS share. For high availability, for agent roles, N+2. That's the requirement. Ensures peak handling even if we have 2 agents offline for whatever reason, whether it be maintenance or whether it be a fault for some reason. Some things to keep in mind. Existing sessions may be interrupted if an agent goes offline. It might be restored because again, that as we talked about, if I go back a couple of slides here, with that Kasm_agent being the manager of it, it's going to be the thing responsible for spinning up images. So if that agent container has an issue and needs to be restarted, the actual session the user is using might still be available, but it might be unaccessible until that agent service is recovered. So it's possible that that thing might still be running even if the agent service goes down. So if I step forward to load balancing, by default, agent servers automatically load balance, okay? It's actually the WebApp role that's auto balancing the agents and the workload between them, okay? So couple of key points here that I'm outlining on this particular slide. The first is they're automatically distributed based on the load balance strategy, which is configured. And secondly, if an agent becomes unavailable, new sessions will be automatically redirected to healthy agents within the same zone that meet the session requirements. So I highlighted these 2 terms of load balance strategy and zone. Let's dive in and kind of explain what those are. So for load balance strategy, by default, and this is just a screenshot straight out of the UI, Kasm does a least load balancing scenario. So what that basically means is if you have, say, we'll just make it simple. If you have 2 agent role servers, right? What it's going to do is automatically put a load on each one of them if 2 users come in. When the 3rd comes in, it will automatically assign it to one of them. When the 4th comes in, it will assign it to the one that only has 1 workload against it, right? So it's going to automatically balance them out and split them out to where everybody gets some load on it. I will tell you that is probably the most costly strategy when we're trying to do this for scaling for price and for trying to keep costs within reason, right? And that's just because if we were doing auto scaling, what would end up happening here is as we auto scale up to accommodate more workload, as each new agent came online, we would immediately allocate 1 workspace to that system, right? And it would continue to do that until we filled up and went up to the maximum number of auto scale agents that we're allowing, right? And so it would never ever actually downscale because we would always try and put at least one server load on them. Now, most loads, kind of the flip side of this, right? Most load is going to continue to load up 1 agent server until it can no longer host anything, right? Its resources are unavailable, and then it would move to the next available agent server. So in an auto scaling event, this would be perfect because it's going to ensure that each one of those agent servers are highly loaded up before it moves to the next one. And thereby, as it downscales, right, it would always try and put things on the least number of hosts so it can spin down any of those added auto scale hosts that got brought up. The other 2 items down here, least Kasm, most Kasm, rather than do it off of consumed memory, which again, least load and most load is, The least Kasm, most Kasm is just going to do that based off the number of sessions rather than the resources being consumed. So at the end, you can kind of pick your strategy on which way you want to do this, basing it off of load and keeping the load as extreme as possible, or keeping the most number of Kasm sessions on one system. It's really just going to depend on which works best based off the type of workload that you have. So if you're using a lot of larger workspaces that consume, more CPUs and RAM, then maybe it's most load that makes sense. If you're doing more of a lightweight browser scenario where you're just doing Chrome or Edge or something like that, then maybe most Kasms make the most sense, and directing the most users to one of those and not necessarily basing that decision solely off of load. But that would be the load balancing aspect of this. And again, by default, out of the box, we do least load. So again, that's the most costly as far as funds are concerned. So stepping forward, we start talking about agent roles and deployment zones. So deployment zones are basically just groupings of resources, okay? These could be specialized workloads. So if we were doing AI development, or you had some machines with specific graphic cards or something along those lines, that might be a specific zone for you. Could be a different geographic zone for you. Could also be a particular, shall we say, private or more sensitive network space that you have access to by workspaces in that area. So maybe there's specific content or something like that within a zone that you don't want to necessarily have available to all of the agent role servers, right? So in our picture here, we're basically just showing that in this case, we have a west deployment zone and an east deployment zone. You'll notice in both of these, we have WebApp servers in each with a load balancer. We have that singular database, but we have resources in each one of these areas. And maybe there's some reason you need to separate them based off of those two geographic locations with zones are concerned. The last thing I'll just touch on briefly is autoscaling. So we've talked about it a couple of times already, but again, just to hammer home what autoscaling is, Kasm has the ability to provision and destroy servers and Docker agents based on user demand. Each cloud provider kind of has their own tools, whether it be, again, AWS, Oracle Cloud, DigitalOcean, GCP. Each has their own flavor of how to interact with it, but ultimately, Kasm has the ability to leverage their APIs to go in and provision and spin up additional resources based on demand. And again, that scaling can be based off of CPU, memory usage, or just in general user demand. Additionally, you can do scaling strategies with this auto scaling. So if you wanted to pre-deploy servers before peak demand happens, so again, envision users coming online into work at 8 a.m. and you want to have this automatically scale out and have, say, rather than your normal 3 agents deployed, say we wanted to scale that up and say we needed 10 available. Then we could turn around and before that peak hour hits, we can have the system automatically auto scale and get those agents stood up, get any required Docker images downloaded on them so they're immediately ready to host and available workspaces for users logging in. Additionally, for cooldown period, off-peak hours, after 5 p.m., we can automatically have this start to scale back and remove those images, or I should say, remove those agent role servers so that we can reduce cost in off-peak hours. Next up, this particular role, I should say, for Kasm Workspaces is the connection proxy. In this one, there's actually 4 different container images residing on these machines. We still have that traditional Kasm proxy for routing traffic to all of the other containers. We have Guac, we have the RDP gateway, and the HTTPS gateway. The sole function of the connection proxy server is to encode connections into WebSocket format for browser compatibility. What does that mean, right? It basically is an optional piece of Kasm that allows and functions as a gateway for users to access resources utilizing traditional RDP, SSH, or VNC connections. These are outside of containers, right? Anything that's coming through this is going to be some other type of server, whether it be an existing virtual machine or whether it be an actual on-prem, chassis piece of equipment. You're going to access that through this. It's going to serve up and make that session and content available. So if we break down what each one of those containers are, first off, the Kasm_guac container, it's a guacamole instance. It's a customized version of Apache guacd combined with a Kasm microservice. Again, web native connections passing RDP, VNC, and SSH servers, right? Passing those connections through it. Kasm spawns a listener node per core on the system with automatic session load distribution across those. The default cluster size for listeners is 4. You can configure that based off of the dash cluster size in node when you're setting it up. One thing I will say, just as a word of caution, do not exceed 8, as we've noticed some instability from the guacd service itself when things get too large, right? So try and keep it at 8 or less. That's ideal scenario for this. So again, guacd just basically allows that RDP session, that VNC session, that SSH session, very lightweight, but allows that connection to come through and be established to an existing piece of infrastructure within your environment. Then we have the RDP role. In this case, Kasm_RDP_gateway. This was something that was added in Kasm 1.16.0. It enables, I should say, client-side RDP connections through to Kasm Windows Workspaces. Really, it could be any Windows workspace, but it allows it through to a Windows workspace. The big deal about it is it's a thick client, right? So because it's a thick client, you can do pass-through of smart cards, USBs, webcams, all while remaining and maintaining Kasm's DLP protections, right? So supported clients through this, of course, are traditional Microsoft RDP clients for both Windows and Mac OS, the Extra Logic RDP client for Chrome OS. Others may be supported, but these are the ones that we support at this time. But basically, this introduces that thick client for USB. Smart card is the big one, right? Pass through. The third container here is the HTTPS gateway. This is, I would call it sort of a companion service to the RDP gateway, okay? So all that's going to do is take all of the functionality back here on the Kasm RDP gateway, and it's now going to take that and proxy it through HTTPS. So what this is ideal for is for that traffic to make it through enterprise firewalls or other security devices. So it's just going to take and encode that over HTTPS and allow that traffic to come through and then be a traditional thick RDP client out to the end resources. It follows Microsoft's remote desktop gateway server protocol, and it maintains all of the RDP functionality in full. But the big thing is it just allows that connection through enterprise firewalls or other security devices that might have a problem with RDP traffic coming through. When we start talking about sizing for these particular roles, right? The big thing is going to be whether or not we're doing session recording, okay? So without session recording, 8 CPUs, 4 gigs of RAM, 80 gigs of hard drive for 32 session connections. If you are going to do session recording, that ups the hardware requirements by basically double. 16 CPUs, 8 gigs of RAM, 112 gigs of hard drive space. Again, for that same 32 sessions, right? Again, when we start talking about this, when we start talking about session recording length, should be about half the number of system cores available to it. So again, 16 cores, we want to have the length set to 8 for that session recording. Disk usage is minimal when we talk without session recording. However, if we are going to bring session recording into it, then you need to plan on that 1 gig of space per concurrent session. You need to monitor I/O in that particular case, because we might have some I/O bottlenecks when we start approaching, 32 sessions. But again, definitely monitor I/O and functionality on those recording sessions. Big thing with connection proxies in general, though, right, is we want to make sure when we configure them that they are all uniform. So we don't want to have any connection proxy servers that are short in resources or over allocated, just to ensure that we have, balanced performance across all of them. As again, these are going to be automatically balanced. So we want to ensure all resources are the same across all of them. So again, for HA, load balancing N+1, allowing for rolling updates with 0 downtime. For our example here, a proxy without session recording, to support 200 concurrent sessions using 8 servers. We need 8 servers, I should say, with that N+1 redundancy. And this setup could support 256 concurrent sessions. During maintenance with 1 server down, it would support 224 concurrent sessions. As always, we want to monitor and scale proxies during peak hours, so that way we know where the load is. One thing I will say about connection proxies in general, that 8 servers for 200 sessions is going to be very much dependent on the type of RDP client that's coming through. So guacd is very efficient, right? There's not a lot of overhead to it. So we can actually get much better performance. We could probably get, rather than 32, we could get upwards of 50 concurrent sessions going through there. But if we're using a thick client, typically, depending on the thick client in question, resources can be consumed. It's less efficient. I'll just put it at that. It's less efficient. So that's why we kind of went with the numbers of the 32 concurrent sessions with these. But definitely something is on a case-by-case basis, and we really need to see what clients and what the workload is the individual user is going to have, and then we can scale based off of that. So that's why, again, monitoring is so key with setting these up. The last role in question here is the dedicated proxy role. The container, the only container that's applied out here is the Kasm_proxy. It is truly just for proxying end user session requests. It's another optional piece to the Kasm platform. Its basic sole purpose in life is for proxying user connections to resources that are closer geographically to the end user to help reduce latency and give the best performance. That is its only purpose in life. So when we look at resource requirements for this, for a dedicated proxy, it's very lightweight. 2 CPUs, 2 gigs of RAM, 50 gigs of hard drive space, should support somewhere around 150 sessions. Disk usage is minimal because, again, it's just functioning for proxying traffic around. That's it. There's nothing stored locally. We do want to make sure, just like with the connection proxy, that all proxies within region should have identical specs, just to ensure similar performance, and that every user connecting through, regardless of the proxy in question, is getting equal performance. HA setup is N+1 again. Again, for dedicated connection, 200 sessions, right? We'd be looking at 3 servers for that N+1 redundancy, which would support 450 concurrent sessions total. And if one system was down, that would drop us to that 300 concurrent sessions. Once again, we want to monitor and scale proxies during peak usage hours, just to ensure that we're really getting an accurate size of what that workload is for traffic. Lastly, just want to bring up all of the ports and protocols here for communication within the platform. So again, we can see end users need to be able to connect through to that web app server. That's going to be, again, our UI as well as the API, not only for systems within the platform communicating to, but also if from a admin standpoint, you wanted to leverage our API to control or manage any configurations, like that would be available. Also, again, the end user should be able to hit the connection proxy, in this case, the RDP gateway, over port 3389 if you are going to leverage that connection proxy with RDP connections. Web app server needs to be able to hit the database, the agent server, and of course the connection proxy of Guac, as well as any VM or hardware for the Kasm VNC, right? Agent server has to be able to hit management server, and the connection Guac has to be able to hit all of those internal pieces, whatever virtual machine or hardware that we're connecting to via RDP, VNC, or SSH. And then, of course, the connection proxy has to be able to also hit the web app server. Again, that's for the RDP connection authorization as well as status checks. And then the connection proxy RDP, again, has to actually send out the RDP connection itself. So let's talk a little bit about what data flow looks like for an actual end user. We've been talking about all of the different roles in question, but let's see how the whole picture starts to come together. So in this data flow model, we're looking at the AWS instance, right? For example, in this particular one. So an end user comes in, hits our front end, they're going to be hitting a load balancer. On the back side of that load balancer is any number, based again off of concurrent user sessions and redundancy, any number of web apps. Those web apps are all connected to a database server. In this case, like I said, could be one of our servers and Docker containers with Postgres and Redis installed on it. Could be a cloud service, could be an existing database or Reddit server that you're reusing for our services. Doesn't matter. But that user comes through, hits web app. They're going to input their username and password. It's going to be validated against the database. They're allowed in. They're going to then be presented with whatever their workspaces are that are available to them, what has been configured for them. Based off of that, whatever they click on, if they end up clicking on, say, a Postman instance, well, they're going to get forwarded off to an agent server to have that fulfilled. And then anything that occurs within that is going to be routed out ultimately to the internet. So let's say it's not a Postgres server in this case, not a Postgres, a Postman instance in this case. Let's say it's Chrome, right? Or a full Ubuntu desktop. When they log into this, they have full access through the internet out through the AWS Internet Gateway. Flip side of this is maybe they're trying to access existing infrastructure or an existing virtual machine within AWS. They're going to come in through that RDP Guac gateway instance, and they're going to connect into their Windows machine, right? And depending on how that is, right, we might be doing a full fat 3389 RDP connection back through the load balancer, back through over onto our Windows system, or it could be just connected through the RDP connection here. It's highly dependent on how that is configured, right? One thing I'll tell you about our numbers here, right? So again, 1, 2, 3, 4, 5, 6, if we're doing here. When we start getting down here to 11 and 12, that's really dealing with if we had auto-scaled Windows agents, right? So if we have, there's a Kasm agent that gets installed on the Windows machine that reports back in and provides functionality within a Windows environment. So this 11 and 12 here is really for that agent connecting in and validating that that Windows instance is up and running and functional and available to receive an incoming user request and for a user to be allocated to it. That's where that little connection line flow there happens. So again, this is a Kasm data flow for a single region. If we step forward and look at a multi-region instance, bit of an eye chart, but let's try and walk through what this really means. So as the user comes in, authenticates in, first off, you're going to notice some things. We're going to have this Route 53 latency-based routing. So what that basically means is as this user comes through, in this case, because we're using Route 53, Amazon is going to do some magic and decide where this user is coming from and which of these two load balancers offers the lowest latency for that user. And based off of that, that is what's going to be served up to them when they hit our website. So depending on where that is, if they hit the West load balancer, then they will end up hitting the West web apps. One thing to keep in mind here is, notice everything in this left box is US East 1. It is the primary region. Primary region because the West web app servers actually exist in the East, okay? There's some reasoning behind that because, again, the web app itself is not really going to be doing anything in the way of performant behavior, right? It has nothing to do with actually the end content the user is going to be consuming. So we want these resources to be here. But again, based off of the decision of East or West, they're going to route through their appropriate load balancer. If they reside in the East, notice both East and West web apps are still going to our same pair of database servers, Redis and Postgres, right? But if they're East, then they'll be being sent out to the East agents for any Dockerized instances. Or again, if they're hitting the East connection proxy of Guac, right? They're going to be hitting East Windows resources. However, if they're getting routed through that West load balancer and that West web app server, the magic that happens here is when this hits, the users are going to get redirected here to another load balancer, but more importantly, to the dedicated proxy server for the West environment. So again, that load balancer is going to have any number of proxy servers behind it, but that proxy server is then going to be doing the connection out to either the Docker instances of the West agent group here, or again, the Guac service, and then ultimately to Windows services. So again, if we go back one arrow, all of these connection paths are exactly the same. Same numbered instances that are residing here, same kind of back and forth flow. The only difference is that this load balancer, right before it, Amazon Route 53 is making a determination, and there's two sets of load balancers. And those two sets of load balancers have two sets of web apps. Those two sets of web apps just have different regions. And when that connection for West happens, it's going through another set of load balancers to that dedicated proxy role, which is the last role that we talked about here. But that's the basics of a multi-region connection data flow. So when we start talking about deploying out Kasm, just a quick little refresh here, right? Our supported OSs are listed here on the screen. For my demo that's coming up, we're using Ubuntu 22.04, but the link above will provide all information on operating systems. Moving forward, when we start talking about the deployment scenarios, right? For a single server, the biggest things to take away, there is no HA and is a single point of failure. All services exist on that singular server. All of them are all Dockerized. They're all underneath that same Docker container, right? And its best use is for 25 users or less, again, that are not key or required for, there's no requirement, I should say, for HA. So again, when the user comes in, hits the browser, here's our singular server with all of the WebApp, DB, Redis, Agent, Guac, RDP, all of those items are listed here. And then you're getting served up with that content here locally. When we step forward, the install on this, we have a very specific link out for the single install document is quite literally as easy as doing the install, only rather than specifying a role, you just say install.sh and it will set everything up locally. You will get the same Kasm UI credentials page at the end of the install process that you would in a multi-server install. And we'll see that a bit when I walk through my multi-server install, but it will contain all of the important information there. When we step forward and start talking about single region deployment, again, biggest thing is services are on multiple servers. Server numbers are going to be completely based off the number of concurrent sessions that you're looking to support. HA is possible in this setup. It's also very much encouraged. I do have a link here on the slide out to the multi-server install, but that's the biggest takeaway here. Additionally, things like direct to agent is possible in a multi-server environment, is not possible in that single server setup. The next step is that multi-region that we talked about on the data flow. Again, biggest thing is all the same benefits that we talked about the multi-server deployment. We do incorporate the use of dedicated proxies in this setup, as well as having agent and connection proxies within each region for resources in each region. But other than that, same basic setup. Now it's time for our live demo of a multi-server deployment. Our scenario for this deployment is simple. We're targeting, again, a single region multi-server deployment, targeting 30 users. Linode is going to be our cloud provider. We are going to deploy out a couple of connection proxies. Additionally, for our databases, we are going to be leveraging the native Dockerized containers of Postgres and Redis that Kasm will deploy for us during install. We're not going to be consuming any existing databases, nor any sort of cloud provided service for a database. Moving back over here, you can see I have the basic breakdown of my 7 servers that I've pre-built for this demo. Singular database with a pair of WebApp servers, a pair of Kasm agent servers, and a pair of proxy servers. I also have up here our documentation for a multi-server deployment. Starting with, you'll notice our network topology here of our users coming in, the required ports and protocols available to them being 443N to hit the WebApp server. And of course, if they are going to leverage those connection proxies we deploy out, then it'll be 3389 as well that they need to be able to connect directly to those proxy servers on. Scrolling down, you'll see our list again of ports and protocols, both with source and destination. So before we really begin any installations here, we need to validate that these are already open and existing, especially if you're using any sort of zero trust network architecture. In this example today, we are just going to be on a flat network, so there's nothing we really need to contend with about communication limitations. Once again, we'd want to validate our system requirements, so like resources. Again, this is an Ubuntu 2204 image. I do already have swap space set up for them. Nothing incredibly strenuous with these. Again, this is just a simple demo environment. So for what our actual install is going to look like, it is going to be as simple as following our guide here. So to start with, on our Kasm database, we're going to cd into the temp folder. I am actually just going to copy and paste these commands in. That will pull down our latest version of Kasm. Now we are going to untar that. Now we're going to execute the actual install of the database. Now you'll notice here we have a couple of variables, right? If we want to custom name the database or the username to access that database, we can specify those requirements here. But in my particular case, we are not going to specify them. We're just going to run with the defaults. So as such, it is going to be as simple as just running the sudo kasm install .sh script with the appropriate role. We need to accept our license. You'll notice we'll have pulled down the container for the Kasm_DB. It's creating, standing them up, waiting for them to launch. Perfect. Now, this selection, after the installation is completed, these are going to be all of our default credentials for accessing not only the front end of Kasm, but also for registering all of our additional servers. So I'm going to copy those out onto just a notepad, just so we have those available. Now we're going to step forward and we're going to deploy out the WebApp role. Again, we'll have two of these. We'll go ahead and install one first, just so I can kind of show you what the UI looks like after one is deployed and installed. You'll notice right up front during our install process, it does clearly state what items we need to have available for information before we begin this process. So again, database host name, the database password, Redis password. Again, if we've modified and created a custom username or a custom database name, we will have to feed those items in there. Additionally, we need to validate that the WebApp role servers can access the database on these two specific ports. So again, you'll notice the install procedure looks very much similar to how we deployed out the database. But this WebApp server is going to be deployed in much the same nature. The only difference is going to be what the role is that we're targeting here. So once again, to start with, we're going to cd into temp. Again, we're going to curl and pull down the install files. We're going to untar those. Now we're actually going to go through and build out our install command. So give me one quick second while I take and insert our passwords and Redis information into the install command. You'll notice we'll be doing a sudo bash, running that same install script as I mentioned before, along with the role of an app server. Our database connection, notice we're using the private network IP for these connections. This is not going to be anything going out the front door, as it were. I've input our database password and Redis password, as well as specifying the swap size. Once again, we'll have a license agreement. It will begin pulling down the images required for this install. Perfect. So now what we are going to do is we are going to pivot and actually log into the front end of Kasm. All right, perfect. So again, for my particular instance here, we are leveraging self-signed certs, so we'll get a security warning here. In this particular case, we are going to accept the risk and continue. Now we will grab our default credentials. Again, these were populated during the startup of the database server. All right, so we are logged in. So as you can see, with just a database and a single web app server, right, we're able to hit the front end of Kasm. Now, if we turn around and look at this and go to look at our managers, you'll notice our single web app 1 is up. Last reported time in was just 10 seconds ago, and it's currently in a running state and marked as our primary. So now what we are going to do is we're going to go ahead and bring our secondary web app online. Again, process is going to look exactly the same. So we are going to cd to temp. We're going to pull down our install files, untar those. We are going to leverage the exact same install string we used before, same connection to the database. Acknowledge our license agreement. Perfect. So we'll refresh. You immediately see that WebApp 2 is in here now. Now you'll notice there's only one primary web app at any given time for a Kasm instance. That's because the primary web app is the server that's in charge of handling autoscale events, anything to do with managing resource generation or reduction, any of those type of events. So it has primary control over it. Now, the way we want to get this working, right, in an ideal situation here within Linode, we would leverage the node balancer here. And I will configure this off camera for the moment. For our actual demo purposes, it's not going to change anything. But essentially speaking, right, we would have that load balancer in front of it. So for our end users, it really doesn't necessarily matter which web app they connect to. One is just going to have preference for managing, again, those autoscale events. But in the event that WebApp 1 goes down, this will automatically fail over and make WebApp 2 the primary manager for handling those events. So in this particular case, that's why we have the built-in redundancy here. But for all intents and purposes, our two web apps are now deployed and operational, and we can step forward with our next server deployment type, which in this case is going to be our agent servers. So as we step forward with our agent server deployments, you'll notice we can just scroll forward here. We have the same sort of requirements up front that our install documentation lets us know. So we need to know what the manager host name is, whether it be the IP, host name, FQDN of the web app server that is resolvable and reachable by the agent server in question that you're deploying. The token that you'll be using to install, again, it's the, might as well call it the API token for registering this as being a web app agent, I should say, not web app, pardon me, but an agent server of the web app server, right? And then lastly, of course, the agent host name IP address that is resolvable by the web app server. Okay, so again, what we'll end up doing here, CDing into temp, pulling down that same tar.gz file, performing the same unpack of it, and then once again, give me a moment to update our manager token. So our install string for our first agent is going to look something along the lines of this. Our role will be agent. Public host name for this would be our 10 address in my particular instance here. Manager host name is the 03 and our token as well as our swap spot. So again, press enter. Yes. One thing I haven't commented on before, but you'll notice it is validating if Docker and Docker Compose are installed. If not, it will automatically pull those items down during this install process. All right, perfect. Again, if we want to validate that has happened, we can come in here to our Docker agents, and you can see our 10005 has now registered. Notice that it is not enabled at this time, which means for all intents and purposes, the resource is there, but we're not actually leveraging and utilizing it. So if we were to set up some workspaces and try and have an end user come in and then try and access something, this system would not turn around and actually serve up that workspace to the end user. So what we will turn around and do is we'll go ahead and repeat those steps on our agent 2. So again, temp, curl, pull down our GZ file, untar it, and lastly, execute our install. Now notice, again, we've updated it, so we're going to be using the IP address of this particular agent server, as well as, again, we'll just connect into the same manager host at this point in time, right? But we do have the updated token for this install, and we're doing that swap space. So again, acknowledge our license agreement. Perfect. So our installation there has completed. If we come back here to Kasm front end, you'll notice we can restart this. I can enable both of these so they can actually host out content at this time. Now what I'm going to turn around and do is a couple of things. I want to stop and go back first off and look at our database server. So if we just turn around and run a Docker PS here, you'll notice we have our Postgres 14 running and our Redis running. You can see all of our network statuses and what we're serving up to the outside to receive connections, as well as the name on those systems. We step forward and conduct the same thing. You can see here on our WebApp servers, we actually have a fair amount of items here running, right? We have Proxy server for routing the traffic around. We have the API server for actually serving up content, right? Connecting into things, right? And then we have the Kasm manager itself for running and serving the session information, right? As well as if we were leveraging anything in the way of shares, right? That container is running. And that's the same thing that's happening here on WebApp 2, right? Mirror images of one another. If we run here on our Agent 1 server, you can see that, again, we have a proxy, again, for routing our traffic around, but then we have the agent, the Kasm agent container. And that's what's actually managing spinning up workspaces on a given target agent server, right? So again, same thing here. Mirror images. Now, what I want to do just very quickly is I want to pivot around to workspaces. I want to pull up our registry here, and I'm just going to do a simple download install of Chrome. And then I think we'll also, let's do something else nice and lightweight that shouldn't take a lot of time here. Let's do Postman. So you'll notice up here, installing 2 workspaces. Estimated size remaining, right? But we're going to go ahead and pull down those 2 items at this particular moment in time. All right, perfect. You'll notice here if we refresh the page, we have no workspaces currently installing. So it's completed the download of those. So if I just run a quick Docker PS again, you'll notice we really don't have anything new to update or share or show there, right? But if we run a Docker images, you'll notice it has gone and pulled down our Postman and our Chrome containers, okay? And you can also notice the exact same thing happened here on our Agent 2. So because right now I don't have anything specific in the way of zones configured, just the default zone, that means anything I assign and create is going to be in this group, and therefore every one of my agent servers should have the same image, so it is capable of hosting that image up. One important thing that I want to bring up here is we see this periodically with some customers. If I go back into registry, let's do workspaces. This enable button here, I want to make it clear that this enable button is just, are we offering up this workspace for users to connect to? Doesn't mean we're eliminating it, right? So what I mean by that is if I switch this off and say we're no longer going to leverage Chrome, right? I'm no longer going to serve that up to the user base. If I go back and look at this images, it's not really going to take and remove that Chrome image. You quite literally need to go in here and delete this off, because if this was an auto-scaling setup that we were doing here, right? And we were going to have our agents dynamically expand and contract, if I have anything listed in our workspaces, even if it's, not enabled, but if I have these images, any and all of my agents as they spin up are going to be required to download these. And so it can do a couple of things. First off, it can slow down the time it takes for this agent server to be ready to host out content for my end users. So that's one effect of this. The other thing, of course, is just size. If I go in and select every one of our available images from the registry workspace here, right, I can very quickly fill 100, 200, 300 gigs worth of storage in images. And if these images aren't really going to be used, then we shouldn't have them listed at all within our workspaces area. So as far as good hygiene is concerned, make sure in our workspaces, we only have what we're actually going to leverage out there. So let's conduct a little bit of a further demo, kind of describe out how, again, our load balancing works. So again, if I go look at our zones at this point in time, and I navigate through, right now, by default, our load strategy is least load. So that means I have 2 agent servers, right? So it is going to take any request for a new workspace, and it's going to put one on one agent server and one on the other. And we can demo that by just coming back in here, going to workspaces, and I'm going to go ahead and open this in a new tab. There's our Chrome tab there. And then I'm going to come back here and I'm going to open up Postman. So I have my 2 workspaces up and available. I can come back in here to my admin panel and I can see from session standpoint, I have my 2 sessions up, and you'll notice each one of my agent servers is hosting one up. Now, in this case, if we go back to run Docker PS, you can see the namespace because I'm using my Kasm admin account. You can see that it's named Kasm admin here. And you can confirm that agent 1 is hosting our Postman. So our Postman instance here. We come over here. You can see again our Kasm admin and Chrome. And of course, it's our Docker agent 2 that's hosting this image. Next, we're going to move forward and set up the proxy servers. So as you can imagine, we come back to our multi-server install. You can see what we're going to need for this particular step of installing a connection proxy server. So again, that manager host name, that service registration token, and then a connection proxy host name as well. But at this point in time, we should be well acquainted with how we deploy out our software. Again, CD to temp, pull down our latest installer, untar it. In this particular case, rather than the manager token, we're going to be leveraging the registration token. So again, sudo bash, our install.sh, our role of guac, API hostname, public hostname, registration token, and swap space. Again, accept our license agreement, and you'll notice this is a very, very, very quick install. All right, so now we're going to install the second proxy server. CD to temp. Pull down the software again, untar it, and we're going to do the install now. Come back over here to our connection proxies area. You'll notice we have our connection proxies set up here, both 7 and 8. You'll notice if we come back up here and look, Docker PS, we again have our proxy server for routing our traffic. We have the RDP HTTPS gateway, the RDP gateway, and the guac server. And that's what's being shown here for each one of those items as well. So with that, Functionally speaking, we have a multi-server, single region installation of Kasm completed. Now, of course, there's much more to fine-tuning your workspaces and adjusting all of those items. That's for an additional course, but at this point in time, you have a multi-server deployed. Again, it's important to remember. Do remember to come to our documentation page. It will go through and outline all of the different items, all of the required parameters for each server being installed, as well as the communication required ports being opened for each of those to connect. The one additional item that I will throw out and scroll down and highlight, I did not deploy in this one because, again, this is single region, but if this was a multi-region install, we would be leveraging a dedicated Kasm Proxy instance. So the install procedures are down here at the bottom. You'll notice pretty much follows the exact same outline that I've already shown with all of our other roles. Only difference is rather than the role being guac for the connection proxy, for the dedicated proxy, it is truly just the role of proxy. And then, of course, you will have some post-install configuration to be done within the UI to complete that. But with that, as I said, thank you for your time. This is a multi-server install completed for Kasm. Thank you.